Okay, so Hugh Postle is giving the last talk of this session.
All right, thank you. Hope you can all hear me. So I'll be talking about linear time and efficient distributed algorithms for list coloring graphs on surfaces. So I thought maybe I would just show you my main result first, and then we'll back up and I'll tell you some history so you could appreciate it. Because there's really one result, and it goes like this. For every surface S, and k in 3, 4, 5, there is a linear time, or if you want to do distributed algorithms, so this would be the local model, a log n round algorithm. It's actually the same algorithm that given a graph of girth at least k, so 3, 4, 5, and an 8 minus k list assignment L of g, so that'd be 5, 4, or 3, this algorithm will either find an L coloring of g, so it'll find your list coloring, or if it fails, because not all such graphs might have a coloring, it will output an L critical subgraph of g on at most linear and genus vertices. So it'll show you a very small obstruction for why this is not possible. So again, linear time algorithm or an efficient distributed algorithm, it's going to be the same algorithm, and it will do this for any surface, in particular for the plane, the sphere. Okay, so again, I'll come back to that, but let me say some history and motivation. So again, we're list coloring, so that's I give you some list assignments. These are assignment of lists to the vertices. I want to color from those lists so the adjacent vertices don't get the same color. For planar graphs, what was known, every planar graph is 6 list colorable. This is easy, because they're 5 degenerate. You can just color them greedily. Margit Voigt, she showed in 93, answering a conjecture of Erdős, that there exists a planar graph that is not 4 list colorable. So the 4-color theorem does not extend to list coloring for planar graphs. However, Thomas in the next year, in a very famous proof, about a page, it's from the book, showed that every planar graph is 5 list colorable. So 5 is the right number there. And that, again, answered a question of Erdős. Now, Thomason's proof, if you go through it, you find that it yields a natural algorithm. And the algorithm is quadratic. It's O n squared time on n vertices, if I give you this 5 list assignment L, to find an L coloring. And a question that had been open then for 25 years was, does there exist a linear time algorithm to find a 5 list? So I give you this 5 list assignment L. Can you do this in linear time to find the coloring? And if you saw my main result there, the answer is yes. So we answered that question. Now, also the theorem, it talks about planar graphs of larger girth. So it's, again, by degeneracy, easy to see that every planar triangle-free graph is 4 list colorable, because they're 3 degenerate. And Margit showed in 95 that there exists a planar triangle-free graph that is not 3 list colorable. So Greuch's famous theorem that triangle-free planar graphs are 3 colorable does not extend to list coloring. However, Thomason showed that if you exclude triangles in 4 cycles, so that would be planar graphs of girth at least 5, that those are 3 list colorable. And once again, there's a quadratic time algorithm if you look at the proof. And once again, you could ask, does there exist a linear time algorithm? And again, that main result I showed you says yes, you can do that as well. So that's planar graphs. What about surfaces? Because the title had surfaces in it. Well, so for that, I'll need another definition. So we'll say a graph G is L critical for a list assignment L if G is not L colorable, but every proper subgraph of G is. And then we'll say that a graph is critical for k-list coloring if you're L critical for some k-list assignment L. Right, so these are somehow the important ones that aren't kind of k-list colorable. And actually, a somewhat easy theorem, Thomason gave a formal proof of this, that for every surface S, there exist only finitely many graphs embeddable in S that are critical for 6 list coloring. And so that's rather easy, maybe a couple pages. With Robin Thomas, we showed that you can actually do this for 5 list coloring. And you might notice the crazy dates there. It takes about 8 papers to do this, about 200 pages to show this. So it's a very extensive work, still getting published. And you can also ask about higher girth. Well, you can show pretty easily that there are only finitely many graphs of girth at least 4 that are critical for 4 list coloring. And I was able to show in a kind of companion work of maybe another 30, 50 pages that for girth 5 you can do 3 list coloring, that there are only finitely many for 3 list coloring. Now, why would you care about those? Well, it has immediate algorithmic implications. Namely, you get the corollary that for every surface S, there's a linear time algorithm to decide if a graph embedded in S is 5 list colorable or 3 list colorable for girth 5. Simply, you just test all the critical graphs, and you can do that in linear time on surfaces. And you can even you can decide if it's actually L colorable for a given assignment L. So you can also do that. So we know how to decide. So that was all that work. We know how to decide if it's possible to color. But can you actually find the coloring? Well, Dvorak and Kobayashi in 2012 showed that there exists an n to the O of g time algorithm to find such an L coloring if it exists for a graph embeddable on a surface of genus G. So that'd be Euler genus. Here it doesn't really matter. Again, if it exists, so you can find it in n to the O of g time. And naturally, they asked, OK, well, surely we don't need this n to the O of g. Maybe there's an n to the 100th algorithm that just works, that does not depend on the genus. Or, I mean, if you really wanted to dream, you could ask for a linear time algorithm to find the coloring. Now, that would be, for planar graphs, when the surface is just a plane, that would be those previous questions. But we solved those, and indeed, we solved this too. So there exists this linear time algorithm to find these colorings that does not depend on the genus, and it's linear time, which would be best possible. So that's about surfaces. So, I mean, I've known this and been working on algorithms for surfaces, but I got interested last year in distributed algorithms for coloring planar graphs, or list coloring planar graphs. So let's talk about what's known there. So here we'll be doing the local model, so where vertices can pass unlimited information in simultaneous rounds. They have unlimited computational power, so really it's an information theoretic question. And Goldberg, Plotkin, and Shannon a long time ago in 1987 showed that there exists an O log n round algorithm to 7-color a planar graph. And Lineal had showed, trees you can't even color with a bounded number of colors in better than O log n. So this would be, not going to hope to do better than log n, but this shows that 7 coloring can be done. And while for 30 years there hadn't been enough progress on this, turns out last year there were 2 papers. So the first one was Chechik and Mukhtar showed that you can improve this to 6-color planar graphs in log n rounds. And you can 4-color triangle-free planar graphs. So those are kind of the 2 easy things I talked about before. 7 coloring is really easy. I mean, just for structural results. 6 coloring and 4 coloring triangle-free, those are easy from degeneracy, but they actually found distributed algorithms. For list coloring, a different group, Albuquerque, Bonamy, Bousquet, and Esperet, they didn't get a log n, they got log cubed n, but they're able to do it for list coloring, to find an L coloring of a planar graph from a 6-list assignment L, and from a 4-list assignment if you're triangle-free planar. So slightly worse bounds, but they can actually do this all for list coloring. Well, OK, so what about lower bounds? What can you ask for? Well, actually, the 4-color theorem will not hold. You won't have an efficient algorithm. So that's a theorem by Albuquerque et al. That 4-coloring a planar graph would actually take at least a linear number of rounds. Now, in local model, you can do anything in linear rounds. So this is really saying you can't do kind of better than trivial. And this just follows from constructions that there are graphs which are locally planar up to distance maybe n over 2 that are not 4-colorable. So it's kind of information theoretic. It's saying, I can show you this graph, or this graph exists. I could feed it to your supposed algorithm, and that algorithm won't be able to decide in less than log n. It won't be able to tell in less than that many rounds that it's not planar. And so it should be able to 4-color it, but then it couldn't, and that's a contradiction. And similarly, there exists a construction that shows that that 3-coloring a triangle-free planar graph would take omega square root n rounds. Because there's omega square root n locally planar triangle-free graph that are not 3-color. Right, so the 4-color theorem, Groitz's theorem, won't hold. There won't be distributed algorithms to do them. So this obviously leaves a somewhat big hole, right? So we can do 6, and we can't do 4. We can't do 3-color triangle-free, but we can do 4-color triangle-free. What's left? Well, do there exist polylogarithmic round algorithms to 5-color planar graphs? Or the other big open question would be to 3-color planar graph of girth at least 5. So this is not even for list coloring, but of course you could ask these as well for list coloring? And the answer is yes. So the main result implies the answers to all those questions. So let me again state the main result. So given a surface, and k is in 3, 4, 5, you get an efficient linear time or log n round algorithm, so actually log n, not even log cubed, that will either find you this L coloring if given this 8 minus k list assignment L, or it will actually even output a very small L critical subgraph. So in the plane, there aren't such subgraphs, so you would just produce the coloring on surfaces. You might find these instead. So it's one algorithm that just does them all. Okay, well, what is the algorithm? And what are the proof ingredients? So that's what I'll talk about in the last half of my talk. Yeah, so what's the connection? Well, in this large, 8-paper series, 200 pages, here's kind of the main theorem that Robin and I proved, that if you have a graph, girth at least k, embeddable in a surface S of Euler genus G, and I give you this 8 minus k list assignment, and I tell you I fix a subgraph H of G, then there exists a very nice subgraph G prime that's linear in the genus plus the number of vertices, with the following amazing property that every L coloring of H either extends to an L coloring of G or does not extend to an L coloring of G prime. A different way to say this is you have a small kernel for pre-coloring extensions. So I can find kind of a linear-sized kernel that has all of the coloring information you want. So to see if a given coloring of H extends, you just look at the subgraph and you test it on that subgraph. And that implies the finitely many results, because critical graphs would have to have these properties, and implies the algorithmic results. Well, actually, with a bit of work, which wasn't maybe clear to us at the time, but with a couple of extra pages, it produces the following corollary. It goes like this. I give you a graph. It's no longer on a surface. It just has girth at least k. But I promise you that every, say, log n neighborhood in the graph is planar. So it's kind of locally a planar graph in terms of distance. Then actually you are 8 minus k list colorable. And that's somewhat surprising, because the point is you would need this corollary to be true to develop these distributed algorithms. But the distributed algorithm result, if you can have a distributed algorithm for 5 coloring planar graphs, it would have to tell you that graphs that are locally planar are actually 5 list colorable or 5 colorable. And we actually had done that, kind of didn't realize at the time, but we could get this. And this is the only proof I know of this theorem. So that's what made me think we should use our theory to do this, because the only way I knew how to do this was from 200 pages of theory, was to get that result. Okay, so you can show the locally planar graphs have this property, but how do you actually get an algorithm to find the color? Well, that took some more work. And that's the point of this talk and this paper. And here's the new ideas we needed. So I need one definition. It's very nice. It says, an induced subgraph H of a graph G is R deletable in G if H is L colorable for every list assignment L, where the size of the list will be R kind of minus the number of neighbors outside of H. So what's the point of this? If you had such a subgraph, you could delete it, thus the name deletable, get a coloring of the rest, and always get promised to extend it in, because you always have a list of that size when you're doing the extension. So it'd be very nice to find these deletable subgraphs. They'd be very good for algorithms. And with some work, so maybe 10 pages, you can take the theory I said on the previous slide and get a stronger version. It looks like this. If I give you a graph of girth at least k, 3, 4, 5, embedded in a surface of genus G, and a subset x of the vertices, and you promise me the graph is big, so it's at least bigger than linear in x plus g, g is the genus, then actually you can find a deletable subgraph, and you can find it disjoint from that root set x. And this immediately implies the kernel thing, because you won't have, if you took minimal kernels, they won't have deletable subgraphs, and so that actually is a generalization of the earlier theorem. But so I'm promising you somehow, if you're kind of big compared to a root set in the genus, that there exist deletable subgraphs. Okay, well, what can you do with that? Well, this is where I tell you about a new structure theorem for planar graphs that it came up with. So you know about separators. A separator graph G separates the vertices into two sets of size n over 3 and 2n over 3. The famous Lipton-Tarjan theorem promises that planar graphs have small separators, square root n. Maybe less well known, but if you know the separator hierarchy, there's a corollary that for every epsilon, there's some constant c, so that a planar graph then actually has a small linear size set, most epsilon n, and every component is small, size at most c. So it shatters into these small size components. And if you think about it, since planar graphs have small number of edges, you can actually guarantee that the vertices in those components also have small degree at most c. So this is nothing new, but let me give you a name for this. We'll call it a C pocket. So it's a deuce subgraph of size at most c and degree at most c and g. So not degree in the component, in the whole graph, small degree. So I'm just saying then, you have a linear sized thing that separates everything into C pockets. So what's the new stuff? Well, for that I need a definition. The co-boundary of an induced subgraph H will be the set of vertices with a neighbor in H, but outside, so not the boundary, but the boundary of the complement. So here are the two things I need. A purse is a connected induced subgraph H whose co-boundary has size at most 2, and when you add the two vertices to H, and you add an edge between them if there are two of them, the result is planar. So a purse is really just kind of a one separation or a planar two separation in a graph. And now I can tell you some definitions. So we'll say a pocket is a purse, a C purse if it's a purse in a C pocket. And we'll say it's D deep if the co-boundary of H is non-empty and has size most 1 over D times V of H. So meaning that there's a lot of vertices inside this pocket, right? That the co-boundary is quite small. Okay, so I need one more definition, then I can state the theorem. So we'll say a wallet is a set of subgraphs of a graph that are all C pockets. They're non-touching. That means not only vertex disjoint, but no edges between them. So they're all non-touching. There's a lot of them, so there are linearly many of them. And we'll say that a wallet is D deep if every subgraph is either a purse or D deep. Okay, that's a lot, but here's the point. Theorem. Well, tell me a D, and I will tell you a C, so that if G is a planar graph, then there exists a D deep C wallet of G. So what does this mean? Planar graphs have structure. I want to say basically planar graphs, yeah, they had these small things that separate into the pockets, but no, I can actually make those pockets deep. So there's a small set of vertices that will break it into pockets. That's actually not true because, I mean, you could just take two vertices and lots of degree 2 between them, but then they'd be purses. So you kind of either get lots of small planar 2 separations or 1 separations, or you get lots of deep pockets. And then that's actually can be extended to surfaces as long as the graph is, say, at least C times G of S. G is the genus. So that can all work. And what's the point is then these are actually deletable. So Thomason's theorems, he actually proved essentially that purses are deletable in this context. And my theorem from before tells you that D deep subgraphs contain deletable subgraphs. They might not be deletable themselves, but they contain something deletable. And if you put that information together, then it shows that you get a deletable C wallet, right? Because everything's a purse, or you can just pass to the subgraphs if they're D deep, and that would still be a wallet. So you're going to get a wallet where everything is deletable. So you get many linearly non-touching deletable subgraphs in planar graphs. And you can do this on surfaces too. And then here's the algorithm. So it's quite short. I mean, it's not hard at this point. If your graph is small, you just brute force determine whether there's a coloring or not. And if there's not, return your critical subgraph. Step 2, you take all of the vertices of bounded degree, and you see if they're in pockets. You take them all together, and you delete them. And you find a coloring recursively. And now we want to extend back. Unfortunately, if I'd just taken a wallet of deletable pockets, which you could do in computate normal complexity, then it would be easy. I would just extend. In the distributed setting, you have to be a little more careful. So what you do is, while you're recursing, you find a coloring of those so as to break them into about C to the 2C different wallets, and then you extend to each wallet. And if something was colored, you uncolor it and extend again and extend again. And in the end, you end up with a coloring. And so in summary, we proved there exists this linear time polylogarithmic round algorithm for finding 5-less coloring, 3-less coloring, girth 5, graphs on surfaces. I think the nice part is developing the structure theorem for graphs on surfaces with purses and deep pockets. Somehow these are the important things. So if you can prove linear bounds for your problems and or for small 2 separations, you could apply this and basically build nice distributed algorithms or linear time algorithms. And strangely, we actually proved that minimum counterexamples to Thomason's theorems and even our crazy 200-page theorems, this all means they have bounded size. There actually exist brute force proofs of them. We just can't find them because they'd be brute force on a million, vertices. But if you had a fast enough computer, you could actually just brute force kind of prove these theorems with about a page or 2 of this separator theorem, which is very strange because, people didn't know if there existed such proofs for Thomason's. And, well, they do exist. They would just be very hard to find. So I think that's where I'll stop. Thank you.
Questions? No, nothing. Okay. So, thanks.